Hello folks, I built an analog to 4-bit decoder, so I'm going to go ahead and walk through it. Once again, this is kind of based on Skater 0's design for the thing. There's some differences. It's expanded to 4 bits, first of all, and it uses furnaces as a memory system for the powers of 2 instead of sampling just a long train of redstone, so it's slightly more compact. Okay, so I got two components set up here. I have the digital to analog encoder. I talked about that in another video, link it in the description, but I'm not really going to talk about it at all now. Besides that, I have these 4 switches that create a binary input, and the compressor encoder thing here just crams them all into one line based on signal strength. And then it goes to the analog to digital decoder shown in blue. This works kind of similarly to the encoder. Basically, it checks to see whether each bit is which each power of 2 represented by each bit is present in an input, and then if it is, it subtracts it, turns on the output for that bit, and then passes it to the next section of the circuit to do the same thing again with the next power of 2. So right now we have the full input go in here. We jump inside, you can see this a bit better. So the full input goes down here. I'll explain exactly what's going on in the circuit in a second. It's kind of hard to see everything in the higher bits. But it checks to see if the 8's there. It's full power, so all the numbers are there. The 8 is there, so it subtracts an 8 and passes it to the 4's section, which is over here, which does the same thing. Checks to see if there's a 4. There is, so it subtracts it. Passes up to the 2's. Checks to see if there's a 2 in there. There is, so it subtracts that. And then the remaining 1 is just passed out to the 1's bit. So each of these cells is built exactly the same. It's just the only difference is what power of 2 is in the furnace. So this is for the calculation for the 2's bit. So I have 16 redstone in each of these furnaces, which I mean, the redstone is arbitrary, but the number is important. So that gives us a 2 in analog. Alright, so in each section of the circuit, the input comes in, and it's passed out to here. Alongside it is the power of 2 we're going to be checking for, so 2 in this case. Both of these things are passed to this comparator here. If this comparator decides that the input is greater than the power of 2, it'll turn on the output, and it passes the input over here. At this point, it turns on a repeater and blocks off this pathway. At the same time, it passes it to this comparator, and over here we have a furnace passing the power of 2 we just checked for over here. This comparator subtracts the power of 2 from the input and passes that input over here. This comparator doesn't really do much of anything. So that goes to the next bit. In this case, it's the 1, so it's just a flat output. And then if we go over here and turn off the 2's bit, for instance, what happens is the signal here is not stronger than the signal coming out of its furnace. So this comparator is not activated, and the output is, or the input rather, is simply passed through this furnace. Furnaces can conduct things, which makes this circuit a lot smaller than it would be otherwise. Anyway, the input is passed across the furnace to this section of redstone here, and then that's passed to the next section. So like I said, each of these sections of the circuit is exactly the same. Let me just get a good overhead of what it looks like. Basically, you just have this tiled 3 times. It's slightly easier to tile them if you have a bend in it, which is why this is built like this. It does, however, make it kind of awkward to hook up all the inputs to the same thing. I built a 7-segment decoder over there that uses this system to drive the 7-segment display, and the busing is a mess, is kind of the only thing. So I would probably recommend straightening it out somewhat. It'll use more comparators, but whatever. That's pretty much it. It's kind of having these two components together is interesting because, like, encoding is so much simpler than decoding. This is like, there are about as many comparators in each computation here as there are in this entire component. It's just so much more computationally intensive to do this. So that's entropy for you or something, I guess. But yeah, so that's how that works. Oh, and then just to show, if I turn off the ones bit, there's just a 0 through here. And if I turn on the 2's bit and have the 1's bit turned off, it'll like, when we try to subtract, it'll turn out to be a 0. So that turns off. But yeah, that's pretty much the whole circuit. Yeah, so if you need to build something like this, this is a pretty solid design for it.